Welcome to all of my students. Today I will deliver lecture number 18, and now unit 2 is on end, and I hope in 3 lectures I will finish unit 2. So in today's lecture I will discuss some about the lattices. I will discuss the type of lattices, the modular lattice, semi-modular lattice, and related results. Correct? So write down the definition. A lattice L is called modular. If for every A, B, C belonging to L, A less than is equal to C implies A join B meets C is equal to A join B meets C. So we say that this is the lattice, this is the partial ordered set, this is a partial ordered relation, this is meet, this is join, and this is called modular lattice, correct? This is called modular lattice. If for every ABC belongs to L, A less than is equal to C, it means that A is related to C. A less than equal to C implies that A join B, bracket close, meet C is equal to A join B meet C, correct? So now I will tell the fact. Let L be any lattice then for any ABC belongs to L such that A less than C, then just I write here such that A less than C then A join B meets C is less than is equal to A join B meets C. So basically this is the fact that you take L be any lattice, correct? Now if lattice is such that when A is less than is equal to C, then A join B meets C is less than is equal to A join B meets C. We have to prove this fact. Proof. Now you see what is given. Given is that A is less than is equal to C, correct? And also A is less than is equal to A join B. Why? See, A join B is what? A join B is the least upper bound of A and B both, correct? So being upper bound, so A is less than is equal to A join B, since it is upper bound, correct? So by definition, so A is less than is equal to A join B. Now see the situation. Situation is that A is lower bound of C, A is lower bound of A join B. So we have A as right. So A is lower bound of A join B and C, correct? So A is lower bound of A join B and C. Why? Because A is less than or equal to C and A is less than or equal to A join B. So obviously, therefore, A is less than or equal to A join B meet C, correct? See, when what does it represent? What meet represents? Meet represents that this is the least upper bound of A join B as well as C. This is the greatest lower bound. This is basically what greatest lower bound of A join B and C, correct? So this is the greatest lower bound and A is the lower bound of A join B and C, and this is what? This is the greatest lower bound of A join B and C, and A is what? Lower bound of A join B and C. So it is obvious that A is less than or equal to the greatest lower bound, isn't it? This is the lower bound, this is the greatest lower bound. So we get this. You term this as equation number 1, correct? This is 1. Now you see, if we talk about B meet C, see, so I'm writing here, B meet C is of course less than B as well as C. So it is less than B and B is less than A join B, correct? Since this and B meet C is also less than or equal to C. See, B meets C is what? This is what? The greatest lower bound. Being greatest lower bound, it is also a lower bound. So lower bound, it is the lower bound of B as well as it is the lower bound of C. And here B is less than or equal to A join B because A join B is what? Upper bound. So B meets C. B meets C is B meets C is lower bound of A join B as well as C. So B meets C is lower bound of A meet B and C. So of course B meets C is less than or equal to, therefore it is less than or equal to the greatest lower bound of A meet B C, which is what? Which is A meet B, A join B meet C, correct? So it is less than or equal to, it is the lower bound. Now it is less than or equal to the greatest lower bound of A join B C, that is A join B meet C, correct? So this is a 2. Now if we see from 1 and 2, what we get? From 1 and 2, see, A is less than or equal to A join B meet C, and also B meet C is less than or equal to A join B meet C, correct? So now if we take A join B meet C, correct? See here what happens. A join B meet C is the upper bound of B meet C, correct? A join B meet C is the upper bound of A. Is it clear? And this is what? This is the least upper bound. This is the least upper bound. So least upper bound is always less than or equal to A join B meet C. Is it clear? Since from 1 and 2 we observe that A join B meet C is the upper bound of B meet C, and from 2 and from 1 A join B meet C is the upper bound of A, correct? So of course A join B meet C is greater than least upper bound of A and B meet C. And what is the least upper bound of A and B meet C? that is A join B meet C is less than or equal to. So in this way, this fact is proved. Correct? So proposition 1.8.3, let K be the sublattice K be the sublattice of the lattice of congruences, lattice of congruences and suppose that rho composition sigma is equal to sigma composition rho for all rho comma sigma in K. For all rho sigma in K, then K is a modular lattice. So basically it is given that K is the sublattice of the lattice of congruences. This is the lattice of congruences, correct? Lattice of congruences. And how it is written subset and how it is written intersection and how it is written in join. Basically, as we know that when we talk about lattice of congruences, isn't it? When we talk about lattice of congruences, this is the lattice of congruences. And if you take any two, for example, take rho comma sigma belong to here, correct? Then rho, what is the partial order? Partial order is basically here. Partial order is the subset, isn't it? So rho less than is equal to sigma implies rho is contained in sigma, correct? Now rho meet sigma is what? This is rho intersection sigma. Rho join sigma is what? Rho join sigma in the case of congruences, we know that it is basically here what it is given. Rho composition sigma is equal to sigma composition rho. Here it is given, and suppose that rho composition sigma is equal to sigma composition rho for all rho comma sigma in K, correct? So as we already know by result that whenever two congruences commute with each other, then the rho join sigma is what? Rho composition sigma. we have proved this in result. I think this result was, just I'm telling all of you, we have proved this result. So basically corollary 1.5.12. Corollary, if you remember, 1.5.12. In corollary 1.5.12, this result we have proved that rho join sigma is what? Rho composition sigma, correct? So basically this lattice is like this. Partial order should be subset sign, containment sign, and intersection will be what? Rho meet sigma, meet will be represented by intersection, and here join will be represented by composition basically. So this is a lattice, correct? Now KB, the sublattice, sublattice means which is a subset of lattice, and it forms a lattice with respect to same partial order. It forms a lattice, correct? So it is a sublattice. So now what we have to do basically, we have to prove that such sublattice is what? Modular lattice. Let K be the sublattice of the lattice of congruences, correct? And suppose that rho composition sigma is equal to sigma composition rho for all rho sigma in K, correct? Then K is what? Modular lattice. So we have to prove K as a modular lattice. So in order to prove K as a modular lattice, what we have to do? We have to prove by definition of modular lattice, we have to prove the same property, correct? That is what we have to prove. Proof. Let alpha, beta, gamma belongs to K. That is the sublattice of CS, correct? Such that alpha is contained in gamma, correct? Now what is our claim? What is our claim? Our claim is alpha join beta meet gamma is equal to alpha join beta meet gamma. This is our claim. For every alpha, beta, gamma belonging to K. Isn't it? If we prove this, then K becomes what? Modular lattice. We have to prove this, correct? See, basically we have to prove these two equal to each other. And by the previous fact which we have done, we know that since by previous fact, what we have alpha join beta meet gamma is a subset of alpha join beta meet gamma. This we have. So this we have. So we show that. So we have to show alpha join beta meet gamma is a subset of alpha join beta meet gamma, or you can say that is alpha join beta means alpha composition beta intersection gamma is equal to alpha composition beta intersection gamma. Basically we have to prove this, isn't it? Since alpha composition beta is equal to beta composition gamma for every alpha beta belongs to K. Therefore, alpha join beta is what? Alpha composition beta. This we have, correct? Also, alpha join alpha meet beta is what? Alpha intersection beta. This we have. So basically, we have to prove that alpha join beta intersection gamma is a subset of alpha is a subset of alpha composition beta intersection gamma.